Okay, students, thank you, Tyler, for hitting that classwork. Okay, there's our outline for today's activity. We're going to collect homework number 1 now. Okay, so get your homework ready. And remember, I'm going to call up one group first by alphabetic order, last names, and that's the group that'll be graded by me. And then after all those guys bring up their papers, then the rest of you will give all your papers, and those will go to Mr. Tyler over here for grading. Okay. So everybody ready? Ready on the left. Ready on the right. Let's go. All students with last names G through M, bring them up to me right now. Last names G through M. Oh, okay, good. That's right, I forgot about you. Just pile them up right here. Put them in a pile. G through M. I see triangles, subtriangles. Oh man, I see right angles. G through M, please. I see people turning in papers, a notebook paper. No, you're supposed to do it on the paper I give you. Uh-oh, I see erasures on that one. That's good. That's good. G through M. No, but you're going to be on my bad list. No candy for you today. Okay, great. Thank you. G through M. What? Down the hall and around the corner. Or actually, it's right out in the hallway here. You'll see it. Just turn to the left. Switch me over to doc cam. Okay, students. Shh, 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 shh. Now, there's a student here. I'm going to obscure the name, but this student turned it in on notebook paper. No! I want it on this page, okay, on the front of that page and one page only. Switch me back over, please. Thank you. All right. Now, I'm not going to take points off today for that, but next time I will. All right. This is it. So these guys, you're on my bad list, but you're not getting points taken off today. And there's a bunch of you. Okay, the rest of you bring yours up here to the front. Just pile them up on the doc cam. No, pile them up over here, please. Yeah, just stack them up there neatly, like nice. Ooh, red ink. Notebook paper. I'll mark you down for that. That's crap. Don't do that. You think you can do that at some job? You can't do that at a job. You'll get fired for that. I can't fire you, but I can mark you down. Okay, homework. Everybody else. A through H. N for November to the end of the alphabet. Okay, Tyler, this is your pile, and I'll talk to you about how to grade this. Dude, who turned in classwork? What's his name? David O'Donnell. You're slacking on me here. Okay, there you go, better. Is that everybody's homework? Speak now, forever hold your peace. Okay, go ahead and keep that in a stack for yourself. Um, and I got mine over here. So, okay. Okay. Now, we're gonna split up into groups in just a few minutes, but before we do that, I want to go through my solution. Okay. So here's our quadrilateral. We already know the specs for it, the distance along each side. We figured out the last side, side displacement vector D. We figured that out on Thursday. And we know the tilt angles for each side as well. Now, the question is, how do you figure out the area of that quadrilateral? And it is not a trapezoid, okay? It's not a parallelogram. It's not a rectangle. It's not a square. It's not a rhombus. It's just kind of a blobby, miscellaneous quadrilateral. So you can't use any parallelicity. Even if it were a trapezoid, at least you have parallel sides, and you can make two triangles and then a rectangle in the middle and figure out the area, or if you know the trapezoid law, you can use that. But we don't have that. We just have, a bunch of angles and stuff. And so now here's my method. And this method is actually the most helpful for us. So take notes on my method. And I saw a bunch of you did some alternate techniques. I don't know if it's correct, but there are different ways of tackling this than what I'm going to show you. So what I did is something that we do, and we use a skill called tessellation, Tessellation. Occasionally we use that in the theory of relativity. And so if you make a rectangle that catches three of the vertices, you can start the problem that way. Now that's easy to figure out, the dimensions. The height of it is the y component of displacement D plus the y component of the bottom edge, that's displacement A. The width of it is just the x component of displacement A. And because that is the case, you can use the displacement A component triangle. There it is. All right. And let me just move it in place. Okay, so one of those triangles out there is actually a triangle that we already know the height and width. Okay, so the 1/2 base times height gives me the area of that. Now, this one over here, you can just slap it right in there. That's the component triangle for displacement vector B. All right. Now, displacement vector C is up here, and this one is kind of the, yeah, I guess this is the component triangle for that. I guess you can call it that. All right. Now we got this little gap up here. We got a notch up here in the northeast corner. That's all right, because that rectangle, base times height, Cinci, right? That rectangle, the width of it is the x component of displacement B, the light blue triangle. The height of that gap rectangle is the y component of displacement C's component triangle. All right, so that's C subscript y. All right. Does that look familiar, Seeley? Where are you at, Seeley? He was on the, we were working on this in office hours yesterday. Another student and I worked it out just this way. And another student came in and it was right in front of him and he didn't twig to it. But this was on the chalk or the marker board yesterday in the office hours. And let me emphasize that coming to work Monday office hours for homework that's due the next day, yeah, not a bad strategy. Okay, because you're studying with me. All right. All right. So we got one more triangle to get to. Actually, let's burn in this. Okay, so here are the two widths and heights, the width and the height based on the two component triangles for displacement B and displacement C. And then let's just give it a little rectangle and place it in place there. And then the last one is the displacement D, the component triangle for it. And so third quadrant vector, yeah, there it is. So now your theory is, all right, I know the big rectangle. It's what it was at 15.67, I think, something like that. And I can figure out the area of all these other colored triangles and rectangles. So that means the leftovers, if I subtract each of those from the big rectangle, I've got this mangy quadrilateral in the middle. All right. So let's take a look at them. Okay, 15.7 square kilometers, and that's for the big rectangle. Let me park this down in the bottom here. Okay, and then just calculate the area for the component A triangle, or the displacement A triangle. It's 1.42 square kilometers. For displacement B, it's 0.81, not quite as big. For the gap rectangle, 0.67 square kilometers. And for vector displacement C triangle, it's 1.40. All right. And then the big one over here is 1.54. That's for displacement vector D's component triangle. All right. So subtract all those colored ones from 15.7, and what do you get? Ding, 9.86. All right. So there's your answer. All right. Does anybody recall getting like 9.86, 9.8 something? Okay, all right, good. I'm glad a bunch of you did. This was not an easy problem, and I'm about to show you some alternate strategies that are not as easy. Now, but let me ask for questions about this strategy. Do you have anything? Don't talk over me, all right? Even with your back turned. Okay, go ahead.
Even if it's just one of the sub-triangles, would you be able to just kind of demonstrate on the dot cam which components we're using to find those areas?
No, I can't do it on the doc cam, yes, but remember we did all those component triangles. We sketched them out anyways on Thursday, and you guys calculated most of them, all three of them actually, to get vector displacement D. This one over here, let me get my cursor over. This one over here is the one that we were trying to figure out on Thursday. So you were staring at it the whole time on Thursday. You just didn't know that I was going to ask you about the area, because what you were doing was figuring out the perimeter.
You're just using X and Y.
Just X and Y components for each of them, because this is the component triangle for vector D. All right, and we had to figure out this X component, so that's dx up here, and this is dy down here on the downstroke. That's what we had to figure out in order to, get that length on Thursday. Now we use it to get an area, 1/2 base times height, and then we do the other ones, 1/2 base times height, 1/2 base times height, 1/2 base times height, and then we got this little rectangle over here, height times width.
If that's the case, then would it not then be the absolute value of those components then?
Yeah, that's correct. Yeah, so you would use you would take, so this one over here, vector displacement D is negative, negative, that's third quadrant, because it's a directed vector going this way. So notice I don't have any arrows on this. And but yes, if you were looking at your components, you would do the absolute value of each of them, you know, or just, mentally drop the minus signs. Because, when you're doing an area, it's always a distance, and distances are always positive. All right.
It's called tessellation.
Yeah, this we've tessellated a rectangle to figure out one of the tessellations on the inside that quadrilateral. By the way, this strategy of tessellation and detessellation exhibits two things. One is that this is an analytic view of it. All right. You've broken down a big problem into 5 subproblems, and then you got to put them back together to get that central area, the purple area. Right? So that's the analytic approach. Break things apart into subunits, figure them out, and then see if you can fit them back together in a way that gives you the answer you're trying to figure out. All right. And the second thing that this approach shows you is one of the ways, in fact, I think this is the way that the Greeks proved the Pythagorean theorem itself, by using not with quadrilaterals like this, but with a right triangle. They showed, they built on each edge of a right triangle a square of exactly that size, and then they figured out how those squares, parts of those squares similar to the original triangle would tessellate the entire, an entire big, rectangle, I think it was. So they did, they did the right triangle, they did squares on each edge, and then they broke them apart and put them back together to form a big rectangle. And you can look it up on the internet, I'm sure. Under proof of Pythagorean theorem. And it's basically a geometric proof. It's kind of nice. And there's various ways to tessellate a right triangle and get it. So I invite you to take a look at that. Okay, question back here. What is your name again? Spell it. A-N-H, An. Okay, An. What do you have? What's your question?
How did you get 50.8 for the area of the big triangle?
50.
How did you get the area for the big
The big 50.7. Yeah, the big rectangle. The big rectangle, look, the height of the big rectangle is dy plus ay. All right. All right. So two components, and as what was your name over here again? Yo, with the specs.
Rob. Rob.
Rob. As Rob right behind you said, take the absolute value. Okay, add those two up, and that gives you the full height. And then this full width, the way this works out, this full width is just the x component of the displacement A component triangle. And does that make sense to you?
Not really.
Well, it's all I can tell you is it's right here. The height of this big rectangle, the big one that encases everything, is a little bit of this, is the height of this triangle plus the height of this one. All right? Because look, go back to this one. Okay, the height of, so there's right down here is part of the height of the big rectangle. All right, now we got to go around all the way around to get the rest of the height. All right, so forget about this over here. Now here's component, or here's displacement D, and we figured we figured out the height and width of that on Thursday, as I mentioned. All right. Now the height of This part here is simply the height of that component triangle. So from top to bottom of the big rectangle is a little bit of A and a little bit of D. And then the width of the big rectangle is the entire width of A. Right? Now one of the things you can check is see if this component, and you guys make a note of this. If you want to check, if you're ultra paranoid, want to double check everything, check the X component here, plus the X component of displacement C, plus the width of the gap rectangle. And that should add up to dun, 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 A subscript X down here. And then you can use a similar approach over here. The height of the yellow gap rectangle plus the height of displacement B triangle should add up to the sum of displacement D y component and displacement A y component. So you can double check. All right. So let's take a look at some alternate methods for figuring this out. Now, I'm not saying that this is the easiest. It requires a little bit of work. But what I'm trying to do is give you practice getting these doggone components and thinking in terms of right triangles, X and Y components. And that's the other thing I like about this this exercise. And actually the perimeter exercise that we did in class for classwork. Okay, alternate strategies. Okay, forget about these babies. And I'm sure a bunch of you have tried drawing internal lines like this. I saw some corner to corner, and you could see there's a bunch of right triangles in there. But the problem is, like right down here, this is not. This is another quadrilateral. And granted, it's got a right angle here, but nothing else is a right angle in there. But you can do it. I mean, it's got a lot of pieces, but you can do it. The more pieces, though, that you have, the greater the probability of making a mistake somewhere. Okay, so simple calculation. If you can eyeball it, it's better, Jennifer. All right, just remember that. All right, so you could do this. And some of the students in office hours were talking about something like this when they walked in. And then we talked more and we got to the tessellation, and basically this thing here, let me go backwards. Went back too far. Go back around the horn here. Okay, so basically this strategy here, where you don't use the outer triangles, but you try to make inner triangles, you can do it, and it's tricky, but it's doable. And I would not want to try to figure out this little quadrilateral down there. But here's another way that you could tackle that specific problem. You could, I don't know if you could break that up into a right triangle. I think it's inevitable that you get a right triangle. Yeah, can you? You did that?
Yeah.
That little blob down there? Yeah, so that corner down, one of the things that I was thinking about, which would be a huge amount of work, is find the equation, y equals mx plus b of each of the four sides, and then figure where all four, and then you got to figure out these altitudes, and that's another four equations, y equals mx. Well, actually, those are fairly easy. Two of them are y equals something, and then two of them are x equals something. So then you got to figure out the intersections, and then from there you can figure out the length of this mess down here, but it's still kind of bodacious. Oh, I also heard some talk around campus yesterday about using the vector cross product to figure out the area of a parallelogram. Now, I'm not going to ask for a show of hands for people that attempted that, and I'm not going to look at it. I'm going to look at the ceiling. But if you were going to try that, that's like, that would, to me, that would be like a mental torture device, trying to use those. So I hope if you did try it, I hope you abandon it quickly. But doing that, you'd have to figure out a bunch of vectors and just the right ones, and it's a little shaky. Now, okay, so another alternate solution is take the component triangles. So there's the A, flip it around, okay, and make it, half inside, half outside. Instead of, like what I was using, I was doing this one out here. Now you could flip it around and put it like that. You can flip this one around, put it there. Flip this one around, put it there. Flip this one, well, that one you don't need, so let's move that out of the picture. And flip this one out. Yeah, and then you got a rectangle on the inside, and I think some of you basically, and that basically boils down to the same problem that we had before with the two altitudes and the two horizontal lines. You got that rectangle and a bunch of inner triangles, but then the way that I've got it set up, this corner down here is still a headache. Which, okay, I can see now you could do a rectangle here, figure out the size of this rectangle, then subtract these two little slivery right triangles, and actually this right triangle here where my cursor is, that is proportional to the component triangle for B, displacement B. And this little slivery job down, is that how you did it? With a little proportional triangle? So you had to figure out the length of this little side down here, all right? Which I guess you can do. It's not too bodacious, but it's a little more complicated, all right? So this one has a lot of parts, but you could do that. Another method that a student talked to me about was something called Heron's Law. And that is a straight formula if you know what you're doing. All right. And but I'm not going to go into Heron's Law because you know what I try to do? I try to remember the fewest formulas and laws and stuff, and then put stuff together. And Heron's Law is nice, but that's like engineers, and you don't want to. Oops. There's a lot of engineering students in here. So yeah, engineering. How am I going to get out of this? Let me back. Beep, 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 beep. Let me back up a little bit here. You memorizing a bunch of formulas is like using a cookbook, and you can't always do it. And if you're trying to do something, especially if you're trying to do something that no one's ever done before, and that's the fun part of being an engineer or a scientist. Scientists, that's all we do. Try to, extend stuff and find new stuff and figure it out. Engineers, they don't always have to do that, but many times they do. If you're an engineer working at Kennedy Space Center or down in Houston at Mission Control or something, boy, and you got lives on the line potentially. Can you imagine those guys at SpaceX and Boeing? At Boeing, they put their capsule in the wrong orbit. So what? So now, and that's a capsule that's supposed to be carrying a couple, 3 men and women, astronauts. And if they're in the wrong orbit, now what do you tell them? Oops. And how are you supposed to get them back down if they're not in the wrong? How you supposed? They're supposed to be going for the space station, and now you got to figure out another. Now you got another. You just multiplied your problems by about 90, because now you got to get them to come down into the right place in the ocean or wherever they land those things, and then and then, have somebody there, the Navy there to rescue. And what if you don't make it? If you made a mistake on the orbit getting up there, what if you make it? You're heading for the Atlantic Ocean over by the Azores Islands, and you crash into the plains of Spain. You know, dead, 3 dead astronauts. You don't want that. So even engineers and stuff, you've got to deliver. If you've ever seen that movie from a few years ago, Hidden Figures. Oh my goodness, that is one of my favorite movies. And that's about a bunch of calculators, human calculators at NASA back in the olden days when they were just transitioning to computers. And the thing about computers is they're only as smart as their programmer, no smarter than that. And so you have to know what you're doing. There's another thing. How do you write a program? So, and I know a bunch of you guys are computer scientists. Raise your hand if you're a computer scientist and proud of it. Okay. So, kind of proud of it. Well, you guys got to teach a computer to do your work for you. All right. And it can't be smart at every mistake you put in. Hopefully the astronaut lands safely if it's a mistake. But, you got, as I said before, if you're working at a shoelace factory, I mean, there's no lives on the line. Just a bunch of little 3-year-olds trip over their shoelaces if you mess up. But if you're working at NASA, that's lives on the line. All right. We're going to do groups in just a second, but before we do, I have a commercial message from SARC. Here is the tutoring schedule. This is also up in the computer. And actually, let me show you. If you go to the page and then go down the page, right here is a thing that says free SARC tutoring. Now that's what we call in the internets a hyperlink. And if you click it with your MOUSE like this, and magically you get a little blurb, and these are the 2 emails I got from the 2 TAs. So they're a little bit different, but equivalent information. And so it's the same as this stuff here. So there's Tuesday. Oh, you know what else? The location, I'll put it on the next time I do this slide. The location is Engineering 1, room 281. I don't know where that is. You guys in engineering know where that is? Engineering 1? That's second floor somewhere. I didn't even know which one is Engineering 1. But this one right next door is Harris. No. That's not next door. I'm in the math sciences building. Anyways, engineering building 1, room 281. And that's for both of them. So hopefully you guys can, and notice there's a session on Thursday and a session on Friday, but nothing on Monday. Okay, so office hours with me on Monday, and then maybe touch bases with these guys Wednesday, Thursday, Friday, and Tuesday with Juan. So anyways, jot those down in your notes. Now, I want to do some groups. Get ready to move. We're going to rearrange the class now. Let me pause the recording. Okay. Okay. Okay, let's get back to work. Um, okay, here's our clicker question. I see 82 of you have answered. Let's stop it. Oh, very good. The answer to this question, you might want to take notes on this. Greatest speed also means the steepest on a position versus time graph. All right, so make a note of that. And that is why Option A is correct, and everybody got that one correct. All right, good. That's basic, 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 basic. Okay, let's do another question. During which time interval is the object's speed the smallest? Now, do not let me catch you napping on this. Tyler, can you open up all these cabinets in back of us? We're looking for clamps to put on a ring stand so that we can do um, pendulum swings. And they're not, I'm pretty sure they're not in the first two bins, but unlock them anyways. Okay, type in your answers. Ten seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Yeah, so most of you voted on that one. And this one, now the smallest speed means the flattest. So the least steep. So that would be up here at the top. And for that reason, this is the time interval for which that is true. And most of you did get that one correct. 78%. Good. All right, next one. If you've done your reading, hopefully you know the answer to this one. This is a little tougher. During which time interval is the object's velocity negative? Can you take this back to the home page? Yeah, use the, no. Keep that on. Keep it, put it back to the laptop. Just take this back to the, just go to the top. Just go to the top of the page. Go scroll up. Let's go home. All right. Okay, great. Tyler, where were those? Okay, great. All right, just leave them there for now. Steven.
How do I know if it goes through?
You get a little check mark. Let me see your clicker. You're supposed to use the buttons. See? Yeah, see there's little, so let me vote again, watch. See now there's a little check that shows up?
Did I not do that?
I don't know what you were doing. I think you were fooling around with it. So. Students, okay, 5 seconds to vote. 5, 4, 3, 2, 1, 0. Great. Let's see what you guys voted for. Oh, very good. You guys did great. Okay. For this one, the negative velocity means a negative slope on this diagram. So that means downhill from left to right. And that's this interval here from 0.7 seconds to 2.0 seconds. Most of you did that. All right. So that's good. And we're going to do some more stuff for chapter 3 here in a minute. I want to do right now, I'm going to pause the recording. You did not get the free $5. You didn't get the free $1 even. Now, $5 are the same paper. They're just the same weight, same mass, everything. And so, you know, but well, you know, some people can't. So, you know, one thing you could say is, you know, these two guys, they couldn't catch a $1. They couldn't catch up to a $1 bill right in front of them. Yeah. Right. Now you're talking fantasy physics because that will never happen. All right. So what we're going to do now is, can you put me back on the right laptop, please? Thank you. Okay. Now we're going to do a little bit of, we're going to go from the free $5 test. And what we're going to do is do some notes on the calculus of acceleration. And can I have this chair, Tyler? Thank you. Appreciate it. There's another one back at the getaway table. Another chair back there that they're not using. Okay, switch me over to the document cam, please. Now I'll embed this in the YouTube. So yeah, or you can sit on that. That's fine. These stupid things. All right. So unfortunately, I don't have my notebook. I forgot it at home. I'd like to say the dog ate my homework, but I don't have a dog. So let me get out a pencil and a red ink pen. Okay, now I'm going to draw it. I'm going to make my notes in pencil. But I'm going to use red up here to start. A fresh piece of paper. Okay. Okay. Calculus of acceleration. All right. And let me draw a sketch of a hand. Okay, and the $1 bill right here. Okay, so there's the $1 bill. And up here, we'll say that the y component of the velocity is 0 at time t equals 0. Okay, at time t equals 0. And we know that a little bit later, the same hand of 5 fingers here, the dollar bill is going to be down here. And, you know, I actually had a guy, I've had a couple, you know, I've been doing this for 10, 15 years, and I've only had 3 or 4 people catch it. It's very difficult. You have to be lucky. You have to try to time it. And I try to do best. One guy I tried to do best 2 out of 3, and he got me on all 3. So, and that was a $5 bill. So, but no, most of the time, you know, so this one's at rest up here. And this one's in motion downward. And so down here, I'll give it a little arrow. And this is V of, we'll just call it T1. So it's downward. And the speed, V of T1, which is, you know, this is the chalkboard boldface vector V. So that means I have a downward vector. And I'm just describing the direction of it here. But it's a vector, so you at least have to put down the direction of it. The speed is, you know, positive. So the speedometer reads, you know, like, you know, 0.5 meters per second or something like that. Now up here, Vy of 0 is equal to 0.00. So let me put that component here. Okay, so this is Vy of time t1. So t1 is later, so t1 is greater than 0. All right, now that's what we were just doing. And the elapsed time, delta t, the elapsed time is later minus earlier. So in that elapsed time, it gains enough speed to drop past the hand, the student's hand, before he can catch it. All right, so that's kind of that's a little bit of notes on what we got there. All right. Now what this means, what this implies, is that v of t as a vector is equal to some vy of t, a function of time, times the minus j hat vector. Okay. In other words, it's downward. Okay, so this signifies downward, and this signifies the speed. And you know, for a vector, the magnitude of it is the speed if it's a velocity vector. If it's a displacement vector, then you would say that's the distance. Okay, and then this gives the direction downward. And this is for a simple free fall system. All right. Now, so what that means is, let's go to the next page. And I'll be putting these images into Instagram. By the way, my Instagram link is linked on the home page on the list of resources for the student. So let's do a slightly different diagram. Okay. Here's my x-axis. Here's my y-axis. And this will be the position of the $1 bill. So I'm going to trace in my $1 bill right here. Okay, so here's my $1 bill at time t equals 0. So y of 0 as a function of time is equal to 0.00 meters in the y direction. Now I'm not going to study the x direction because it's just going straight down. And down here at y1, so y1 is the position at time t1. It's going to be negative, like 2 inches or something. No, it's more like, how long is a dollar bill? That's about 4 inches. So negative 4 inches, maybe. All right. And then let's go down another 4 inches. So y2. Y2 is the position on the y-axis at time t2. And so how much further down is it? Well, if we say that this is minus 8 inches, then then these two line segments are the same size. All right. But if we say that t2 is some other time, some multiple of t1 or something else, we've got to figure out the distance. All right. Now, the basic idea here is that the vertical position is a function of time. And it's in free fall, so it's changing. We also know that velocity is a function of time. And it's also changing. Now, what does that mean? Well, y of t is some function of time. We're going to figure it out in a minute. And the calculus of this is that the velocity, and I'm just going to call it v now, is the derivative of dy by dt. All right. And so that is the limit. Well, you guys all know about limits. They have a little blurb in chapter 3.2, I think it is, about limits. But so you have you basically have this derivative relationship. Now, the inverse relationship is this, that y of t is equal to the integral from 0, and we'll call it, we'll put it here, time t, of v, and we'll call it t prime, the integration variable t prime. Okay, so there's your, and plus maybe a constant. All right, so you have to differentiate, and actually it's a specific integral, so we don't need a constant out there. So now this thing is changing with time, right here. All right. So we want to get y of t, but we can't because we don't know what v of t is. All right. Now v of t is the derivative of the position as a function of time. Now acceleration as a function of time is simply the change of v over delta t, and in the limit that goes to dv by dt. All right. And that means that v of t is the integral from 0 to t of a of t prime dt prime, with t prime being my dummy variable for the integration, right? So the idea here is that the differentiation here is kind of the inverse of the integration over here. Same thing over here. Now, we don't know what the derivative of the velocity is. We don't know what dv by dt is. All right. So Galileo said this. Let's study free fall under the following assumption: as if a is a constant. Okay, and he was able to measure that. In the metric system, that acceleration is negative 9.8 meters per second squared. And it turns out he was right. And his assumption about free fall was that the velocity always comes in the same size chunks for every second of time that it's in free fall. Let me repeat that so you can write it down. It acquires the same amount of downward speed in every second. In every tenth of a second, smaller amount of speed, but every tenth of a second, it gets the same amount. Now, in a tenth of a second, it'll get negative 0.9, it'll get 0.98 meters per second of speed downward. Okay? In 1 second, it'll get 9.8. Every 2 seconds of free fall, it'll get 19.6, etc., etc. So, this was Galileo's assumption, and it was a good one, and it actually works out. And it happens to be the simplest assumption that you can make about the time behavior of the acceleration. Now, the exception of that is if you're out in space, far away from all the planets and stars and stuff, there's no gravity, you're just floating out there, acceleration is 0 out there. But if on the surface of the Earth, he made this guess, and it worked out really well. He was trying to figure out what cannonballs do. You know, can a ship of the Navy of Venice, for whom he worked, take out a ship from the Empire of Constantinople, okay, the Ottoman Empire, or whatever. I don't think those were Ottomans back. Maybe they were. All right. So can they hit a ship? He wanted to know, can they hit a ship with a cannonball? So he said, let's think of this and then work out everything else. All right. And so let's work everything else out. All right. So let's go to the next page. So A of t is equal to minus 9.8 meters per second. All right. I.e. negative 9.8 meters per second squared. And that's the acceleration due to gravity. It's usually symbolized g. That's the acceleration of gravity due to that's the acceleration at the surface of the Earth due to gravity. And it's basically due to the gravity of the planet Earth. And it doesn't matter what the mass of the object is. If it's a cannonball that he's dropping from the top of the Tower of Pisa, or a musket ball, or a BB, or a pebble. All right. Now, if he drops feather, the feather gets a lot of air resistance, so it takes a lot longer to get down. But he said, look, if everything has the same acceleration and that acceleration is constant, they're going to hit the ground at the same time. And that was his famous Leaning Tower of Pisa experiment. All right. So this is his assumption. Now, let's integrate. V of t is going to be equal to the integral from 0 to t of a of t prime dt prime. Okay, so that's going to be the integral from 0 to t of negative 9.8 meters per second squared in parentheses dt prime. Okay, so this is going to be equal to, all right, negative 9.8 meters per second squared, comma, t prime, evaluated between 0 and t. All right. Now, you lose one term, and plus a constant. So let's put a constant in here now. All right. And because we lose a little bit here because in this, we're starting from rest. So we're assuming that we're starting from rest and that v of 0 is 0, but it doesn't have to be that way. So this is going to be equal to negative 9.8 meters per second squared times t plus or minus a constant. All right. Now, what is this constant? Well, so this is v of t. V of 0 is equal to c, and we'll call it. We can, it could be plus or minus a c here. It doesn't really matter. Okay. So v of 0 is a c. All right. So this formula, v of t, in all its specificity is this. V of 0, whatever downward velocity it had at time t equals 0, minus or plus a negative 9.8 meters per second squared times t. All right, so we now have the function v of t. All is klar. Everything's squared away. All right. Now, hopefully you've seen that in high school physics before, but now with the calculus. All right, now we're doing the calculus of it. All right, let's integrate this baby. All right, now we want to get y of t. All right, so let's go. Y of t is going to be the integral 0 to t of v of t prime dt prime And we go to the next line for this. That's going to be equal to the integral 0 to t of this big mess v of 0 plus negative. You know what? I'm just going to put in g for symbol now. All right, so I'm going to use gt. Okay, and g is equal to this stuff up here. So this just, as with many physicists and scientists and engineers, you're lazy. You like to use symbols and stuff for shortcuts if you use it a lot. So we're just going to go gt. So here's your integrand, and that should be a t prime there. Okay. Now, this is a constant. It might be 0 if you're starting from rest, but if you're not starting from rest, it's good. All right. So let's integrate. We get v0 of times t. Okay, so that's the first. That's the integral of this first part. Okay, now the integral of this t prime dt prime. What's the integral of that, or the antiderivative? Integral of t prime dt prime. Come on, you guys. That should be second nature. T squared over 2. 1/2 t. So this is going to be, okay, and I've got my g out front. 1/2 g t squared plus my constant. All right. So that's y of t. All right. Now let's get that constant specified. We'll just set y of 0 equal to this constant here. So y of 0 is equal to c. All right, so now I've got, now I don't have to have this mystery component. I can fully specify it. Y of t is equal to v0 of t, v0 times t, plus 1/2 gt squared plus y of 0. Okay, and actually what I should write that, this is probably a better form. Y of t equals y of 0. So your initial y coordinate plus your initial y velocity times t plus the change that the extra distance you get from free fall. So that's 1/2 gt squared. All right. So this is the most general formula now using calculus. And this differentiates out nicely. Y prime of t, you cut out the constant, v0. And then what's the derivative of 1/2 gt squared? Gt. All right, that gets you back up to here. All right, and right here. Right here. So it all differentiates out nicely. Question?
From the first integral that you do, you have the first constant c.
Mm-hmm.
Would you not have to integrate the first constant also?
Yeah, we could have done that. Yeah. Mm-hmm.
Okay, so
but see, what we're doing here is we're integrating a differential equation. All right, so we're attaching the constants here. All right.
But if you're taking into account that it already has a displacement in the beginning, you have to integrate that.
Yeah, but it comes out here. We're saying that it comes out here. I mean, you've got a little bit of leeway about how you do these derivatives and stuff. And I just mentioned something called differential equations. Here are the differential equations. Dx by dt derivative is the function v of t. They're coupled, so dv by dt is equal to a of t, and that's also equal to the second derivative of, or actually this should be y. But similar equation holds for the x coordinate. Okay. So this is really what we're working with here, this equation. Okay, so a of t equals the second derivative of the y component over time. And those are what we call differential equations. In other words, equations that have different derivatives. Raise your hand if you're in a differential equations class right now. Anybody? Yeah, a couple of you. So you guys are, this is like ultra cinchy. In a differential equations class, you get really, really fancy. And we'll be doing some fancier differential equations classes when we get to oscillation. For instance, here's for oscillation. Here's a sneak preview of coming events. Oscillation has a differential equation that looks like this: d squared y dt squared. This is for vertical equals y of t. So the function y is equal to or proportional to, I'll put an alpha out here, proportional to the second derivative. If you have something like that, then you know you're going to have sines and cosines. Why is that? Well, because d by dt of a sine of omega t, what's the derivative of the sine? Minus cosine? It's cosine. Okay, so this, and then the omega comes out because you have, so you have an omega and then cosine omega t, right? And then d by dt of cosine of omega t is equal. Now this one, the derivative is minus sine, correct? Okay. So minus omega sine of omega t. So then if you try to put it into this formula here, you have, you differentiate sine twice and you get minus omega squared, you know, when you do all the math here, times the sine of omega t. And that's an oscillation. And this is an oscillatory system. And it's typified by this particular differential equation. Now we're going to get to that towards the end of the semester. This is free fall up here. This is fairly basic. All right, let's look at the x coordinate. Okay, so if we're, get me a tennis ball. Where are the tennis balls? Here, in here. Grab me a tennis ball. All right, give me one of those soccer balls. All right. Now, I have in my hand a soccer ball. And in my other hand, I have tennis ball, right? Now, we've got it squared away if I just drop it straight down. It's right up there, okay? But what if, you ready? What's your first name? Yanal. Y-A-N-A-L. Yanal. You ready? Gonna catch this one? Yep. Right, now I'm gonna toss this one to Yanal. We'll see if he's got butterfingers or not, okay? Okay, because you're not supposed to use your hands in soccer. Unless you're the goalie. Okay, so you're the goalie for the day. Okay, so here we go. Yay. He got it. Okay. Yes, Yanal. All right, so now that, I threw that with a little bit of horizontal velocity. All right. Toss that back to me. All right. And he threw some horizontal velocity and a little bit of upward. Now I'm gonna toss it with a lot. You got to judge to see. You know, I don't want it to bump into the ceiling and everything comes crashing down on. What's your name again? Kirsten. And I don't want her to get conked on the head. All right. So yes. All right. So that was a little bit more vertical velocity, but pretty much the same horizontal velocity. All right. Now, yo, with the brown hat. No, don't turn around. What's your name again? Tannis. Okay, Tannis, you ready? Now you're going to get this one. All right. Now I'm not going to do a bank shot off the ceiling. So I'm just going to try to. Now this one I have to give it a little bit more velocity this way. So be ready. I'm not using my heater, but I put a little more heat on it. Okay. Okay. So here we go. Okay. And notice that it arced upward a little bit, but not a whole lot because I had to get a good long distance. And the further you. Okay. Go ahead and toss it back. One-handed. Okay. Tannis, good. Everybody give Tannis and Yanal a hand. Very good. Nice. All right, now, so we got to figure out the horizontal component of the motion. Now, let me ask you a question. And this might sound like it's from a Bugs Bunny cartoon. But is there a such thing as horizontal gravity? In other words, a gravitational force that goes sideways? No. What? Technically, yes. Now you got to explain that.
I mean,
But he's up here at the Bob Euchre seat, so you can get away with this.
I
Okay.
mean, anything has a gravitational force. You have a gravitational force on me. I have a gravitational force on you. But Earth is a lot larger than anything else, so that's why you only count Earth. Anything with mass has a gravitational force.
All right, let me revise my statement. Is there such a thing as gravity perpendicular to the vertical that goes through the center of the Earth and straight out from the center of the Earth? Is there anything perpendicular to that in gravity? No, there's not. So let's just say that I'm right and that there's no such thing as horizontal gravity. All right. Now that means that there's not going to be any Galileo's the one that figured this out too. So if you're like on a tabletop and there's no friction and and it's horizontal, in other words, perpendicular to the line segment that goes from the center of the Earth straight out towards space, it's perpendicular. If you're on that horizontal plane, you're not going to be gaining any more speed. You kick it off, and then if it's frictionless, it just keeps on going. Okay. So there's no horizontal gravity, and we're going to assume no air resistance. Technically there is a little bit of air resistance, but we're going to ignore that. Where did that soccer ball go? Oh, okay. All right, so let's take a look at horizontal. Okay, so no horizontal gravity, All right. Did I spell that right?
Yeah.
All right. So now you're famous, man. You're going to be on the internet. You're going to be on YouTube. Sweet. All right. So what that means is that dvx, I'm going to start putting in components now. dt, that's the acceleration in the x component in the x direction, is 0. All right. So I'm not going to have any t squared in my x component. We're going to try to get x of t. All right. But I might have some initial Vx. Okay, and so in other words, we might have a little bit, if I just toss the soccer ball to Yanal, we'll have to put on a little bit of heat to get all the way over to Tannis. All right. And if I want to get to those guys at the getaway table in the back, I might have to use the heater. Okay, but I'm not allowed to use that in the city limits of Orlando, so everybody's safe. The public is safe. So you might have a little bit of this. Now that's going to be a constant, all right? Because if v of x is equal to a constant plus, some other function of time, like it's not going to have a t squared, but it might have a t in it. This will differentiate out, and you'll still be, left with this. All right. All right. Now, there's no, oh, wait a minute. We don't even have anything, we don't have any of that because there's no such thing as horizontal gravity. So we don't have that. So v of x as a function of time is simply vx of 0. Right? So whatever you start with on the surface of the Earth, within reason, if you're not like at 11,000 kilometers or 11 kilometers per second or something like that, escape velocity, that's going to be your Vx of t. So whatever you start with, you keep. You don't lose any because there's no horizontal gravity to speed you up or slow you down. Now, if you're on the way up, gravity, if your velocity is on the way up, I mean, think about it. When we toss the ball up, I lost speed on the way up. It got really slow up towards the top of the curve, but then it started getting it back. So if you're on the way up, you lose speed. But if you're on the way down, you gain speed because the acceleration is downward. You're always losing. If you have positive speed upwards, you lose it. If you're on the way downwards, you get more of it. Okay, but we don't have to worry about that for horizontal. So y of t, or no, x of t is just going to be whatever x was at the beginning, x of 0, plus vx of 0 times t. All right. And this is the derivative, or this is the integral of the line up here, the line above. All right. So here's your basic equation of motion for the x component. And this is for free fall. And Galileo figured all this stuff out. He had to do battle with in absentia with Aristotle in absentia. And he defeated Aristotle, whom Galileo revered Aristotle, but he showed that Aristotle was actually wrong, which is good. All right, so let's make a compendium of what we've got. X of t, I'll write this in pen. Is this good? Yeah, okay. X of t is equal to Vx of 0 times t plus x of 0. All right? So that's equal to speed times time. And your horizontal speed is always the same. It doesn't change. All right? Because there's no such thing as horizontal gravity. Now, with vertical, you definitely have some changes. Let me rewrite this one. It should be like this. It's a little bit more helpful for us. Okay, it's a little bit more helpful form. So now this one, y of 0 plus vy of 0 times t plus 1/2 gt squared. All right. Now let's think about this for a minute. All right, so there's my compendium of the two. Now these are the equations of motion for a free fall, an object in free fall. And an object in free fall, this will work for a baseball that we toss across the room, or a cannonball. This is what Galileo figured out. All right. From these two equations of motion, you can get Vx of t by differentiation. D by dt of x of t. All right, and that's just Vx of 0. You can also get Vy of t by differentiation, d by dt of the function y of t. And that's equal to your initial upward speed plus gt. And don't forget, g is equal to negative 9.8 meters per second squared. You got to be careful about that. Now, sometimes you don't. You can use just regular positive 9.8 meters per second squared. So this is calculus, but what does it look in terms of a physical? Well, we know what it looks like. It looks like an arc through the air, but is it a parabola? And so the next question for us, is it a parabola? Parabola. And you know the classic form of a parabola is y equals something times x squared, right? Now the problem here is we don't have an x squared in this. This is a time equation, all right? And this one is a time equation up here for x of t, all right? So we don't, this is geometry class, all right? All right, that's geometry class, right? And what we've got is physics class up there, up here. All right, so we got to figure out some way of, we've got to connect these, we've got to connect this equation up here with this equation down here somehow. How should we do that? Any ideas? Oh, way back there on the bad boy table. Wait a minute. Garcia. First name? Sean. Okay. Okay, this is going to make up for not catching the dollar bill, if you get it right. Solve for t. Which of these two equations would be easier to solve for t? Anybody? X of t is probably easier because it only has t in the first degree. This one you could do it, but it requires quadratic formula. So we don't want to do any of that if we can sidestep it. All right, so let's try to do this. Let's try to follow Sean Garcia's path, the path of destiny. And what we're going to do for simplicity, we'll assume x of 0 is equal to 0.0 meters and y of 0 is equal to 0.0 meters. In other words, the origin. All right, now that makes x of t even cinchier. So here's x of t, and that's going to be equal to Vx of 0 times t. All right, now Sean says solve for t. All right, just got to divide both sides by Vx of 0. So x of t, well, let's just call it x now. Vx of 0 in the denominator, and that's equal to t. All right. Sean, what's my next move? Are we done? Does that prove that I've got y equals constant times x squared? Or anything like it? plug in this thing here. What should we plug in, and where should we plug it in? Any ideas? Think. Come on, that's what I want you to do. That's what you're paying money to do, thinking. Wait a minute, what's your name again? Cathan. Substitute it in what?
Substitute x over v of x 0 for t in your y equation.
All right, let's try it. So let's put it in here. Let's put it in this baby up here. All right, so here we go. And I'm going to drop the y of t now. Y equals, okay, y of 0 is 0. So v y0 times t. Now I'm going to put in x over vx0. So this is x over vx of 0 plus 1/2 g. Now I'm going to put in t squared. All right. So I'll put in t and then square it. X over vx of 0, quantity to the tooth. All right. And so that's equal to vy of 0 over vx of 0 times x plus 1/2 times g over vx of 0 squared times x squared. All right. Now this is not, that is second degree, but it's not quite as simple as this. All right. So, but what does this remind you of? Vy of 0 over vx of 0. Does that strike you as anything? Yeah, it looks like a rise over a run. But it's not rise over run. But let's draw a picture of a baseball down here. All right. And just give yourself a horizontal or a kind of a tilted. Now here's v of 0 as a vector. Okay. Now that means that here is your pair of components. And I just kind of made a generic angle here. This is Vx of 0. And this is Vy of 0. All right. And this is the launch angle theta. And you know, if you're throwing a football downfield, or if you're trying to make a 3-point shot, you know, getting the angle right is important. So theta is important. All right, now let's look at this again. What does that ratio look like to you? What? It looks like tangent of theta. All right, so this is actually tangent of the launch angle theta. And that's a geometric, and that's related to this, the geometry of this launch angle. All right, now this one over here is a little bit harder to explain physically, but when we get a little bit deeper into potential energy and kinetic energy, you'll see that this is actually potential energy all over the wazoo here. And kinetic energy. You see it? You see it here? Potential and kinetic energy. Yeah, we'll be seeing this thing. So it's this is going to be a ratio of potentials and kinetics. It's pretty interesting to think about. But basically we've got a parabola here. Now, okay, tangent theta, nice, times x. So we basically have got y equals beta x plus alpha x squared. But we want to get, you know, well, let me call this gamma x squared. But we want to get y equals alpha x squared. All right. So how would you tackle that problem mathematically? What's your first name again? Brandon? Brandon.
So you want to get these, you didn't want the x
Yeah, we don't, this is true, but we want to get it into something like this. And actually, y equals alpha times some x prime maybe, quantity squared. So what are you thinking? No, well, we want something that will, this will handle any kind of a slanted flight. We don't, straight up is easy. Just straight up and straight down. No x component. We got x's in here. We want to use them. How do you get this into something quantity squared? So that's what we're looking for. Some number maybe times a bunch of stuff with x in it, quantity squared. Dee 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 dee. Pom pom. All right, who's got an answer? Who's got a strategy? Anybody here ever been in Algebra 2 back in the day? How do you handle this? How do you handle it other than tearing up the paper and crossing it out or getting your dog to eat it? Starts with the letter S. Okay, what do you think? You could factor out an x, but that's not all that you need to do. There's another whole procedure for dealing with this. Complete Kaylin. Da, na, na, na. She wins Jeopardy. What do they call the last stage? Final Jeopardy. You win Final Jeopardy. Complete the square. All right? Complete the square, and you'll be golden. All right, now. We were gonna go a little bit further, but this is good enough for today. Let me scoot over here. I'm gonna need some more. I want you. Okay, I want you to. Can you go back to the laptop, please? We were going to do an experiment with a meter stick. We'll do that on Thursday. First thing. That's good. We won't have any classwork to turn in today, but we'll have some classwork on Thursday. Also, I'll be handing back your exams Thursday, or not your exams, but your homework. And I want to talk to you about grading. Hold on, we're not done yet. Okay, so what I want you to do is to read up to chapter 3.4, skim the rest of the chapter, and complete the square. Get me y equals bunch of stuff with x in it, quantity squared. And then that'll be lovely. All right? And I'll talk to you guys on Thursday. You're dismissed. Complete the square.